Hello and welcome to the Optimization in Engineering, Scalar and Multi-Objective course. This module is the introduction to applied optimization in engineering. So, what are the contents of this video? We will first try to describe which are the characteristics of the engineering optimization. Then we will define the concept of extrema or analytical functions. After, we will see how using gradient information we can define a point-based optimization loop. Eventually, we will show how this approach has some limitation. We will introduce two basic concepts that will be important in the following of the course, that is, exploitation and exploration. So first, the main ideas about optimization problem. Engineers are often called to find a new configuration of a design problem, showing better performance than those of a given existing design. For instance, an airplane with a shortened wingspan carrying the same number of passengers, or an airplane carrying the same number of passengers with a lower fuel consumption. So actually, we need to improve our design starting from some existing configuration. The design is usually described by some quantitative values, so for instance, each configuration of our airplane is described by some parameters that are called design variable, usually called X, or degrees of freedom, of the optimization problem. The performance indicator, F, is what we call the objective function of the problem, as we were mentioning, for instance, the width of the wings or the consumption of the fuel or some other function that depends on the design variable. In scalar problem, we need to minimize or to maximize one single objective function. In vector or multi-objective programming, we have to perform the optimization of several functions at the same time. Usually, the union of design variable X and objective F is called the design space. As the optimization process often recalls the search for a trail in a rugged terrain, the shape of the objective function is frequently called the function landscape. Now, we start looking at the minimum of a function, and we start with a very simple one-dimensional function because we can introduce some concept on it. For instance, look at the parabola, so define it as f equal to x squared. What we have in this example is a very nice function because it is a convex function. So actually, if you take 2 points on the function and connect them by means of a straight segment, all the function value will lay below this segment. So this particular convexity property tells us that the function has only one minimum, and this minimum is located where the first derivative of the objective function is 0. We can easily obtain the first derivative, that is 2x, and we can see that where the derivative is 0, and then we know that this is a stationary point, where the function has one extremum point. How can we define which kind of extremum is? We have to look at the second derivative of the function in that point. If the second derivative is positive, then we know that this is a minimum. Let's look, for instance, to another function, for instance, a cubic function. Here it is a little bit more complex because what we have that our derivative is 3x squared minus 1. If we plot this derivative, we see that we have 2 points where the derivative is 0. If we are going to look at the second derivative, we see that on the point on the left, the second derivative is negative. So actually this is the maximum, while on the point on the right, the second derivative is positive, and then it is a minimum. So now analyze another function. For instance, let's say that we have a function and we know its first and second derivatives. We can see, for instance, in this case, we have 3 points where the first derivative is 0. And if we are going to look at the point on the left, the second derivative is negative. So actually here we know that it is a maximum. On the point on the right, the second derivative is positive, thus we know that this is a minimum. When we look at the central point, the second derivative is 0. Thus, it is neither a minimum or a maximum, but we have an inflection point. In the end, even if the first derivative is 0, we must check that this is an extremum by having a close look at the second derivative to understand what is the nature of our point. We have to say that actually these are points that are minimum or maximum of the function, but locally, because actually if we see our function goes to minus infinity where x goes to minus infinity and goes to plus infinity when x goes to plus infinity. Obviously, in an engineering problem, we cannot have this kind of situation because we are usually constrained on our variables. So actually we can't have an airplane wing that is infinitely long. So actually real problems are constrained, and so actually this concept must be adapted to our constraints, but this is explained in the study material. Then let's try to see to a very simple but meaningful problem of optimization where we can formulate the looking for the optimal point. Let's say that we are woodcutters and someone brings us a log of a tree and we have to cut from this circular log that has the diameter d the rectangular shapes A times B. Approximately, we know that the strength of the first moment of a rectangular beam S is equal to A times B squared. So actually the vertical dimension of the beam is much more important than its width. So actually what we can say is what is the beam with the highest strength that we can cut out of our log? So the optimization problem has a constraint, a geometrical relation between B, A and D. Because if we apply the Pythagoras theorem, A squared plus B squared must be equal to the diameter D of the log squared. So actually we can express B as a function of A so that B is equal to the square root of D squared minus A squared. And then we can do some algebra. We can define S as A times B squared, but we already have computed B. So actually in the end what it comes out that S, the strength, is equal to A times D squared minus A cubed. So something that is very similar to one of the functions that we saw before. Now we must apply some calculus to compute the derivative, the first derivative. This means it's D squared minus 3A squared. And if we go to look over at the points where ds over dA is equal to 0, what we have is A is equal to D over square root of 3. So actually we can check that this is a maximum. And if we check the second derivative, we see that it is negative. So QED. Our approach gave us the optimal, so we know that we can't have any better beam out of this log. So now we have to move from univariate function of only one x degrees of freedom to multivariate function, where we have more than 1 degrees of freedom. So what it is usually our engineering problem have more than 1 degree of freedom, and so actually we must use x, y, or z, or more frequently we can call them x1, x2, x3, and xn. Now x is a vector of degrees of freedom, x1, x2, and xn. And if f is differentiable, which unfortunately does not hold for our engineering problem, but if it is differentiable, then f over the x must be substituted by gradient of f with respect to x. This means an array that has in each of its position df over x1, so the partial derivative of f with respect to x1, arriving to f over xn. Things are even worse in the second derivative, because the second derivative must take into account all the interaction between the first derivative along all the other directions. So the second derivative becomes a matrix, what is called the X-Shan metric, and it takes in its ijth position the second derivative of f over respect to xi and xj. So actually the matrix is symmetric, it is n times n square matrix. So in our problem, if we are lucky enough to have a two-dimensional problem, we can make some visualization. And we will try to do this whenever it is possible. So if we have the iso-level lines of our function, we know that the gradient of the function is orthogonal to the tangent at the iso-value line. If we want to maximize our function, we must go in the direction of the gradient. If we must minimize the function, we must go along the direction of minus the gradient. So now let's think about our engineering optimization loop. So in our engineering optimization loop, it is seldom that we have this analytical definition of the objective function. Sometimes we have, but anyway, many times our function comes out of the numerical simulation of our system by means of numerical techniques. So, for instance, by finite element method or circuit analysis or whatsoever. So actually what we have is that usually we start from one configuration, so what is called x0, that is our starting configuration. And we start evaluating f. And then we see, okay, is this f good enough for us? Usually it is not. So what we don't have convergence. So we say, okay, this is not the good place, so generate a new x. And then evaluate again the f. As we will see in this generation of new x values, we will use most of the concepts that we introduced, so the gradient, the Hessian, and so on. Here is where our optimization strategy will work. Then we go in this loop until we find some kind of convergence. For instance, if we are looking for the minimum, we know that the first derivative is 0, the second derivative is positive, and then we say, okay, we found the minimum. So we are looking for x that is the optimum one. We must now introduce two concepts, and they will be used very often in the course. And these concepts describe how we generate the next x. The first concept is exploitation. That means that we use a technique that tries to squeeze maximal information from the points we already have evaluated to refine our search. So for instance, we compute the derivative, the Hessian, and we try to move very quickly to the minimum. On the other side, we have exploration. Tries to see instead if there are other regions that are more promising than the one that we are been sampling with our points. So actually, these two approaches are different, and we try to highlight when exploration and exploitation are important. Now, if we know by hypothesis that our function is a convex function, and we know that it has only one minimum, exploitation will work very well. But for instance, in this case, we have two minima. So one is the good one, that is the global, and then there is another local point where the function is locally minima. So actually what can happen is that if we look at this function with the iso-value lines on the two-dimensional map, what you see that if we start from point P1 and we just go downhill, maybe following some rules that are more or less the minus gradient of the function, we end up in this green point. That is more or less the point where the gradient is 0. So you'll say, okay, maybe you already know the second derivative. Let's say the Hessian is positive definite, and you say, okay, that's the minimum. But what if we have started from P2? So if we start from P2 using the same approach, we can end up in the blue point. And again, it is a minimum, but this time it is the global minimum. So actually going on only with exploitation can lead us to miss some very useful points. And this is what happens if the functions are not convex. So this is what we will see in the next video. Thank you for your attention.